In this video, we begin our discussion on how to estimate using confidence intervals and how to conduct hypothesis testing for difference of two population parameters. Along the way, we will discuss how to estimate a single population mean and also how to conduct hypothesis testing regarding the same. To begin, I would like to give a quick reminder of what the two areas of inferential statistics involves. One is confidence interval estimation, and two is hypothesis testing. So our interest is to look at an unknown population characteristic and to find the best estimate of that population parameter based on sample data that we have, and that starts us up with getting a point estimate. Then, using the method of what confidence interval estimation, we specify the level of confidence that we want to have about using the point estimate and its standard error in finding a range of plausible values of the unknown population parameter. We illustrated this in earlier videos or earlier lessons regarding a single population proportion. Then we went over to hypothesis testing, where we make claims about a single population proportion and we set up the hypothesis, the null and the alternative hypothesis, and we conducted a test to see if the sample data provides sufficient evidence to reject the null hypothesis in favor of the alternative or to fail to reject the null hypothesis. So, as a quick reminder of what we've done, here are two scenarios in these examples. The first scenario or example says the research question is, what is the average amount in dollars spent on meals by students at MCPHS each week? In analyzing which method to use, confidence interval estimation or hypothesis testing, we realize that we're trying to find an unknown amount. In that case, we're trying to estimate something that is unknown. This will call for confidence interval estimation. Confidence interval estimation, since we're trying to estimate a certain unknown value regarding the population of all students at MCPHS. On the other hand, for the second scenario, the trade magazine QSR routinely examines what? Fast food drive-through service times. Their recent research indicates that the mean time a car spends in McDonald's drive-through is 167.1 seconds. A McDonald's manager in Salt Lake City feels that she has instituted a drive-through policy that results in lower drive-through service times. A random sample of 70 cars results in a mean service time of 163.9 seconds with a standard deviation of 15.3 seconds. To determine if the policy is effective in reducing drive-through service times, what statistical method should be used? Take note here that the McDonald's manager feels or claims that the new policy that has been put in place has resulted in a lower drive-through times. This is an instance of a claim, or what we otherwise call a hypothesis. Well, to check if that claim is valid or not, we need to test it, which means that the correct statistical method to use here will be hypothesis testing. So, in inferential statistics, as we established in the first lessons in this class, we will be looking at confidence interval estimation and hypothesis testing. We're going to take that over to looking at differences in two proportions. In other words, if we identify a population A and a population B, let's say the population A is the population of all students at MCPHS, and population B is the population of all students at another university X. Our interest might be what is the proportion or fraction of MCPHS students who own a private car compared to the proportion of students at University X who also own a private car? What is the difference between them? So we have the proportion or the fraction of those in population A who own a car and the proportion of those in the other population who also own a car, so that we're not comparing what other kinds of proportions. We stick to proportion of those who own a car in the first population and the proportion of those who own a car in the second population. Now, as it stands, we would like to examine this difference in proportions. We can examine that difference using the method of confidence interval estimation, or if we have an idea of what that difference should be, we could test if that value that we hypothesize is a valid value, a plausible or reasonable value, or not. Now, we're going to start with looking at the underlying assumptions behind estimating the difference between two proportions, either using confidence interval estimation or hypothesis testing. That will be one, independence extended, which requires that the data must be independent within and between the two groups. And this is generally satisfied if the data comes from a randomized experiment. Secondly, we have the success failure condition, which usually holds for both groups, where we check successes and failures in each group. More to come on that. Then if those conditions are satisfied, the standard error of the difference is given by this formula. The good news is that we're going to deploy the power of technology to help us do these computations. So without any further ado, let's take an example. In this example, we would like to first focus on confidence intervals for estimating the difference between two population proportions. Here is an example. We consider an experiment for patients who underwent CPR for a heart attack and were subsequently admitted to a hospital. And the patients were randomly divided into the treatment group. That would be this group right here. Those who received a treatment, where they received a blood thinner treatment, and those who were the control group, who did not receive blood thinner treatment. Well, the outcome variable that was being measured is whether the patient survived for at least 24 hours after what? Either getting the treatment or not. So our interest here, the outcome variable, is the survival rate in each group, whether be it the control group or the treatment group for 24 hours, for at least 24 hours. Well, our interest here is to create and construct and interpret a 90% confidence interval for the difference in survival rates in the CPR study. So the first step is to check whether we can model what the difference in sample proportions using a normal distribution. The first step is to check for independence of the two groups. This ties well with the requirement pointed out earlier. And how do we check that? It suffices to note that this is a randomized experiment. It is randomized because patients were randomly divided into the two groups, the treatment group and the control group. And based on that, we can say that the requirement of independence of observations is met. Then we have the success failure condition in each group. What does that require? Well, for the success group, that will be the survival group. As far as this context is concerned, you will notice that each of the values 11, 14, 11, and 14, and the failure counts to 39 and 26, these are all equal to or greater than 10. So with that, this condition is satisfied. This 10 is a threshold value that is very important for the results of this analysis to be correct or to hold true. So a reasonable model or a normal distribution model for the difference in sample proportions is considered reasonable. The next step would be to find a reasonable estimate based on the sample data that has been summarized here. And to do that, I would usually like if we compare the treatment group first, the proportion of survival in the treatment group, which is 14 out of 40, to the proportion of survival in the control group, which would be 11 out of 50. So, getting out our calculator, that would be equal to 0.35 minus 0.22. That gives us a point estimate of 0.13. That value we can see here if we use StatCrunch. So, other vital statistics that we're going to need from this summary data, we can get it using StatCrunch. So I'm going to go over to StatCrunch, and in StatCrunch, you go to Stats, and then you go to Proportion Statistics. This time we have two samples from the treatment group first, and then the control group. So we have the summary statistics for each of the samples, and we are required to input the proportion of success in each of the samples. For the purpose of this class, I am going to like if we key in the data values for the treatment group first. This is purely based on choice. You can always key in that of control before what treatment, but I want treatment before control. So in this case, I am going to key in 14 out of the total of 50, out of 40. And so 14 out of 40 versus 11 out of 50. So here we go, 11 out of 50. And my goal is to construct a confidence interval. So I'm going to click on the radio button for constructing. What is the percentage? 90%, that is 0.90. So I'll adjust this. I like to show the critical value and simply compute. And you will see that the result that is right here, 0.13 that we just computed, has been computed to by StatCrunch. In addition, it computes the standard error, the critical value, and the lower and upper limits of the confidence of the 90% confidence interval for this difference, which is right here. Okay, and with that said, let's see. What do these two values mean? A 90% confidence interval for the difference in survival rates goes from negative 0.0271 to 0.2871. So what does this mean? This means that we are 90% confident. We are 90% confident that treatment with blood thinners makes a difference of between negative 2.71% and 28.71% on the survival rates of patients who underwent CPR for a heart attack. Now, it is very crucial we note this. You will notice that we went from a negative value to a positive value, which means we crossed over zero. So because 0%, because 0 is contained in this interval, we can imply that there will be times when the difference in survival rates could potentially be zero. If it could potentially be zero, talking about the proportion of survival in those who receive treatments and the proportion of those who did not receive treatments, If the differences in the survival could be zero, that might be telling us that our treatment sometimes may not make any what difference. So because zero is contained in this interval, we conclude that we do not have sufficient information in the sample data analyzed to conclude that treatment with blood thinners help or harm heart attack patients who underwent CPR. This is very, very crucial. 1-0 lies in that interval. It be an indicator that the effect of treatment with blood thinners might have zero effect. Let us consider a different example where zero is not in the interval. So here's an example that says that a 5-year experiment was conducted to evaluate the effectiveness of fish oils on reducing cardiovascular events, where each subject was randomized into one of two treatment groups. This time, our outcome variable is heart attack outcomes, where we have two groups, those who were treated with fish oil and those who just received a pretend medication called a placebo. Now, we're interested in incidence of heart attacks. Take note that if treatment with fish oil makes any difference or has a reasonable or statistically significant effect, then we anticipate that the proportion of heart attacks in the group with fish oil treatment should be lower than the incidence of heart attacks in the group that received a pretend medication with no real health benefits. So we begin our analysis, and our goal is to create a 95% confidence interval for the effect of fish oils on heart attacks for patients who are well represented by those in the study. I would like to interpret our results. We begin by the reminder that the outcome variable of interest is how often do we see heart attacks in each of these what groups? It could have been no event, but in this case, we have chosen heart attack for the purpose of illustration. We're going to assume that conditions for um, constructing a 95% confidence interval are met because first, we have a randomized experiment that guarantees the satisfaction of the independence requirement. Then two, each of the values for success and failures are all they're all at least 10. So we begin with our analysis. What is the best estimate for the difference in heart attack rates across both groups? I would like, as usual, my what? My proportion of heart attacks in the fish group. So that will be 145 people, 145 out of 12933 versus in the placebo group, it was 200 heart attacks out of 12938. So getting out my calculator, what do I have for that computation? That would be 0.0112 approximately minus 0.0155. So that will give me about negative 0.0043 approximately. Well, we can go again back to StatCrunch to see how we can get all the vital statistics that we need for this analysis. So I'm going to close out of this, go back to statistics, proportion statistics, true sample, and with summary. And in the first group, I have 145 out of 12933. And in the second group, I have 200 out of 12938. And the interest is to compute a confidence interval, a 95% confidence interval in particular. I like to see the critical values and compute. And the result I have here is what we have here in our notes. So I'm going to go back to the notes and let us bring some meaning to this. Our goal was to construct a 95% confidence interval for the effect or difference that fish oil's treatment makes on heart attack incidences. So our goal here, our point here is that the results we have, the upper and the lower limit, so we can say that we are 95% confident that treatment with fish oils reduces or increases. Let us see what that means. Take note that our point estimate was to look at proportion of heart attacks in the fish oil treatment group minus proportion of heart attacks in the control group. If we are going from a negative value to a negative value, it means that we are saying small and then what? And then big. And by that I mean only a small number minus a big number can give negative values. These are strictly negative values. So that means that the proportion of heart attacks in those who received fish oil treatment was smaller than the proportion of heart attacks in those who did not receive fish oil treatments. So that means that it brings down treatment with fish oil brings down the proportion of heart attacks from those in the control group to those in the fish oil group. So we're 95% confident that treatment with fish oils decreases heart attacks by as much as 15%. And where did I get the 15%? That is this value right here. Remember, we're talking in terms of negative values, but if we want to write them in positive values, we flip them around. So you have by as much as 15%, rounding this guy up to 0.15% to 0.71% over a 5-year period. And that applies to patients who are well represented by those in the study. In other words, they're similar in characteristics to those involved in the study. Now, because 0% this time is not in the study, it is very obvious then that the difference in proportion of heart attacks between the two groups cannot be zero. That means that the effect of treatment with fish oils is far off from nothing, far off from zero. That we can say that the data provides statistically strong evidence in favor of the claim that treatment with fish oils supplements reduce the incidence of heart attacks in patients like those in the study.